Good morning, dear students. Welcome back to physics class. Today, I would like to present the topic Elementary Concepts of Differentiation and Integration for Describing Motion, Part C. The subtopics are A. Acceleration and B. Graphical representation of motion, various graphs. You know that velocity of an object along a straight line when it is in uniform motion is constant with respect to time. In this case, the change in velocity of the object for any time interval is equal to 0. But in non-uniform motion, the velocity varies with respect to time. It has different values at different instant of time and at different points of the path. The change in velocity of an object during any time interval when it is in uniform motion is equal to 0, but in non-uniform motion will be not equal to 0. This change in velocity of an object is represented by small letter a. For today's class, I have introduced you a new physical quantity which is nothing but it is the acceleration, which is defined as the rate of change of velocity with time. The average acceleration a over a time interval is defined as the change of velocity divided by the time interval. Average acceleration a is equal to v2 minus v1 divided by t2 minus t1, which is equal to delta v by delta t. It is the mathematical expression of average acceleration, where v2 and v1 be the instantaneous velocities or simply velocities at time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. You have to notice this point. In uniform acceleration, change in velocity per unit time is constant, and in non-uniform acceleration, change in velocity per unit time is not constant or variable. From the VT graph, which is the velocity time graph shown in given figure, figure number 1, where we have represent time along x-axis in second and velocity in y-axis in unit of meter per second, we can obtain instantaneous acceleration, which is acceleration at every instant of time. Here we have used the concept change in velocity divided by corresponding time interval, which is equal to v2 minus v1 divided by t2 minus t1 is equal to delta v by delta t. It is the average acceleration. We can draw acceleration time graph from velocity time graph. Figure 2 shows the resulting acceleration time graph or AT graph, where acceleration is represented in y-axis in unit of meter per second square and time t is represented in x-axis in unit of second. We see that the acceleration is non-uniform over the period 0 seconds to 10 seconds, that is, its value is varying between the time 0 seconds to 10 seconds, but it is 0 between 10 seconds and 18 seconds. And it is constant with value of minus 12 meter per second square between 18 seconds and 20 seconds. When the acceleration is uniform, obviously it equals the average acceleration over that time interval 18 seconds to 20 seconds. You have to understand that the average acceleration is obtained by the slope of velocity time graph. We have to determine the slope of the velocity time graph connecting the points. They are y coordinates and x coordinates corresponding to v2 t2 and v1 t1. We can determine the average accelerations for three different intervals of time. First interval of time 0 second to 10 second, average acceleration a is equal to 24 meter per second minus 0 meter per second whole divided by 10 second minus 0 second, which is equal to 2.4 meter per second square. Second time interval is 10 second to 18 second. The average acceleration a is equal to 24 meter per second minus 24 meter per second whole divided by 18 second minus 10 second, which is equal to 0 meter per second square. Here average acceleration is equal to 0. And third time interval is 18 seconds to 20 seconds. Average acceleration is equal to 0 meter per second minus 24 meter per second whole divided by 20 second minus 18 second, which is equal to minus 12 meter per second square. It is the negative value which is the average retardation or deceleration. This is the method to draw AT graph from VT graph. You have to note this point. Instantaneous acceleration can be defined in the same way as the instantaneous velocity which you studied in earlier class. So, you have to remember the definition of instantaneous velocity now. Instantaneous acceleration is represented by small letter a, which can be mathematically written in the form of limit delta t tends to 0 v2 minus v1 divided by t2 minus t1. It will be equal to limit delta t tends to 0 delta v by delta t is equal to dv by dt, which is the equation number 1, where dv by dt is the rate of change of velocity with respect to time t, where v1 and v2 be the instantaneous velocities at time t1 and t2. Delta v be the change in velocities, that is v2 minus v1, and delta t be the change in time, that is t2 minus t1. The instantaneous acceleration is the slope of the tangent to the velocity time graph at that instant in such a way that we have determined the instantaneous velocity by finding the slope of ST graph, which is position time graph of a moving body. From previous class session, you studied velocity is a vector quantity because it has both magnitude and direction. And also, you studied from 9th grade class, a change in velocity is caused by either change in magnitude or direction, or both magnitude and direction of velocity. So, acceleration may be resulted by a change in magnitude of speed, or a change in its direction, or change in both magnitude and direction of speed. Like velocity, acceleration can also be positive, negative, or zero. Positive time graphs for motion with positive, negative and zero acceleration are shown in figures A, B and C respectively. Note that the graph curves upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. You have to notice this point. Acceleration can be variable with respect to time. When you focus to study of motion with a constant acceleration, you have to consider that the average acceleration of a moving body is equal to the constant value of acceleration during any time interval. Then consider the situation of a moving object whose velocity at a time t is equal to 0 b v0 and velocity at a time t b v. Then what should be its average acceleration? Average acceleration A is equal to final velocity minus initial velocity divided by change in time, which is equal to v minus v0 divided by t minus 0, which gives v is equal to v0 plus at, which is the equation 2. You have to understand that the slope of velocity time graph or Vt graph of a moving body gives acceleration. This is one application of velocity time graph. Slope is determined by this mathematical expression, which is y2 minus y1 divided by s2 minus x1. Here y2 as v2, y1 as v1, s2 as t2 and x1 as t1. You have to put this y coordinate and x coordinate values. You will get the slope of the graph, that is delta v by delta t, which is the acceleration of the moving body. If a body is uniformly accelerated, the graph will be slope up or uncurved with inclination, which is shown in given figure. To determine the slope of the graph AD, you have to use this expression, which is the slope is equal to dc divided by ac. Here change in y coordinate values be the change in velocity, which is represented by dc, and change in s coordinate values, which is change in time, represented by ac. Then slope is equal to dc divided by ac, which is equal to v minus u divided by t minus 0. So acceleration A is equal to v minus u divided by t. Now let us see how velocity time graphs for motion of a body with constant acceleration change in following 4 cases. First case is motion in positive direction with positive acceleration. You have to consider the example of previous body whose motion between t is equal to 0 second and t is equal to 10 second, whose acceleration time graph is given on right side. Second case is motion in positive direction with negative acceleration, which is represented in figure B. You have to consider the same object whose motion between t is equal to 18 second and t is equal to 20 second. Third case is motion in negative direction with negative acceleration. Suppose a car moving along negative s direction but with increasing speed. What is happened? it has negative acceleration, but it moves along negative x direction because of it has changed its direction, that is, it is reversed, which is given in figure C. And fourth case is motion of an object with negative acceleration that changes direction at time t1 and moves in the opposite direction till t2. For example, motion of a car with a decreasing speed along positive x direction and turning back and moving with the same negative acceleration. That is, it moves in the opposite direction between the time intervals t1 and t2. Which means that car direction will be changing after the time t1, which will be continued till t2. When it moves along the positive x direction, it has decreased its speed. After the time t1, its direction has changed but continued to move with the same acceleration, that is, negative acceleration, which is shown in figure D. Let us see second application of velocity time graph. Area under velocity time graph gives displacement of the object over the corresponding time interval. This is second application of velocity time graph. As shown in figure, the graph is a straight line parallel to the time axis and area under it between t is equal to 0 and t is equal to capital letter T is the area of the rectangle whose length or base is equal to t minus 0 is equal to t second and breadth or height is equal to u minus 0 is equal to u meter per second. Then what should be its area? Area enclosed by the graph with respect to x-axis or time axis is equal to area of the rectangle is equal to length into breadth, which is equal to u meter per second into t second is equal to u into t meter per second into second is equal to ut meter, which is the displacement in the time interval 0 to t second. Next, I am going to discuss on very important features of graphical representation of motion. Here, it describes three graphs, which are position time graph, velocity time graph, and acceleration time graph. This slide shows a table with the criteria and the descriptions of these various graphs. First criteria is x and y axis. For the position time graph, they are time and position. For velocity time graph, they are time and velocity, and acceleration time graph, they are time and acceleration. Second criteria is slope. For position time graph, it represents velocity of an object. For velocity time graph, it represents acceleration of an object, and for acceleration time graph, it represents the jerk or push of a moving body. Third criteria is straight slope. For position time graph, it represents uniform velocity. For velocity time graph, it represents uniform acceleration, and for acceleration time graph, it represents uniform jerk. And fourth one is curvy slope. For position time graph, it shows change in velocity. For velocity time graph, it shows change in acceleration, and for acceleration time graph, it shows change in amount of push or jerk. This slide shows position diagrams for different motions on object. First graph shows object which is in stationary state. Second graph shows object in uniform motion, and third graph shows object initially at rest then uniform motion before coming to rest again. This slide gives velocity time graphs for different motions of objects. First graph indicates the object is a stationary object. Second graph shows that object in uniform accelerated motion, and third graph shows that object is initially at rest then uniform motion before coming to rest again. And acceleration time graphs or AT graphs for different motions of objects are given in this slide. First graph indicates object which is in stationary state. Second graph shows that object in uniform accelerated motion, and third graph shows that object initially at rest then uniform accelerated motion before coming to rest again. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.